How exactly do airbags save lives during a vehicle collision? To find out, you'll need to understand momentum and impulse. Let's explore the science behind this life-saving device and how that science relates to life on the International Space Station. Let's go! Hi, I'm ESA astronaut Andreas Mogensen. In the microgravity environment aboard the space station, even though we appear to be weightless, momentum still exists because it depends on an object's mass and velocity. An object's mass doesn't change whether it's in space or on Earth. We regularly monitor our own mass on the space station to support ongoing health research. In microgravity, we can't weigh ourselves on a traditional scale. The Space Linear Acceleration Mass Measurement Device is one tool on station that can help measure our mass using momentum. To define momentum, we use this equation, where P, or momentum, is equal to mass times velocity. We can see any object with mass that is moving is considered to have momentum. Impulse, on the other hand, is equal to the change in momentum of an object. Now, about that airbag question. In the event of a vehicle collision, an airbag decreases the amount of force exerted on the human body by increasing the amount of time it takes for the body to slow to a stop, resulting in fewer catastrophic injuries and more lives saved. For example, I have an inflatable globe that is initially stationary. If I apply a net force to that globe, I am causing a change to its velocity, which is thereby changing its momentum. During the time I applied the net force, the globe experienced an impulse. This can also be defined as force times the amount of time for which the force was applied. Okay, here goes. I'm going to gently set this globe in motion so that it hits this firm, rigid surface that I'm standing on. Did you notice how fast that collision happened? It was almost instantaneous. In other words, the time from when the globe made initial contact with the surface to when it came to rest and then suddenly changed directions happened during a very small amount of time. If we were to look at the impulse equation, you'd notice that time and force have an inverse relationship. This means if one variable decreases, the other must increase. In this case, the small amount of time caused a large force to be exerted on the globe. Let's try a different scenario, where we have a loose curtain set up to catch the globe instead of a hard wall. Once again, I'm going to set this globe into motion by gently pushing it towards the curtain. In this case, so that it is moving at roughly the same speed as before. Notice that it took more time for the globe to come to rest after its initial contact with the curtain. Remember that time and force are inversely proportional, meaning that when a collision occurs over a larger increment of time, the globe experiences a smaller force when compared to the earlier rigid surface demonstration. Hey Space Center Houston, catch this and try it yourself. Nice throw! We enjoyed having you with us to learn a bit more about the relationship between impulse and momentum. Can you think of another situation back on Earth where the momentum-impulse theorem could be used? To test out what you've learned today, try the corresponding classroom connection activity that you can find at nasa.gov/STEMonstrations. Thanks for exploring physics with us today. See you again soon.